In this chapter, we continue exploration of smoothing techniques, and one of the most, as we said, it's one of the most popular and flexible families of forecasting methods. And smoothing methods rely completely on averaging past values to reduce random noise in the data, which allow us to better detect the underlying patterns. And as we said, it's data-driven techniques, all of them. We don't assume any assumptions. So in this lecture, we are going to discuss multiple exponential smoothing techniques. One of the first and most basic one is the SES, Simple Exponential Method. It became one of the most widely used in business forecasting because it balances flexibility and easy of use. It's like moving averages. It's data driven, as we said, and smooths out the noise. But the difference, instead of treating recent points equally, it uses exponentially decaying weights. In other words, recent observations matter more, but old observations are never completely ignored, but we still use them. So it's kind of adaptive more than the moving average. Also, there is something, it's the assumption. It's like the moving average. We assume that no trend and no seasonality. It can only model the level of the series. If we have a trend or seasonality, so it will fail. It doesn't work. So we apply, as we said before, differencing and deseasonalize before we apply this method. So, but we assume having no trend and no seasonality. It has multiple formats, mathematically speaking. The first formula, as you see, it shows the weighted average of all of the past values. It's unlike the moving average. Where the moving average, we had a finite window. Here, the window is not, we do not look at the window, actually. We just add all of the series, but with different weights. If you look at the alpha, we have alpha is the smoothing, we call it the smoothing constant, which is 0 and 1, between 0 and 1. And to do forecasting, if you look at the values, we have YT, the previous actual value, YT minus 1, the one that before, YT minus 2, etc. We go back in time, but we multiply everyone by a factor. This factor called smoothing constant, which takes values between 0 and 1. And here multiply by alpha, here alpha times 1 minus alpha, and so on. And the recent observation, it depends on the alpha, but generally speaking, if you multiply, if alpha is 0.1, so this is going to be 0.1 times 1 minus 0.1, 0.9. So it depends on the value of alpha, where you are putting the weight more, right? If alpha is big, so you are putting weight more somewhere here. If alpha is small, it's the opposite way around, and so on, right? The second formula I would like to talk about is the error correction form, which is this one. I call it, okay, the SES is an active learner. So each new forecast equals the previous forecast, but we adjust this one using the error. So it's the new forecast equals the previous one plus the error multiplied by alpha. And what is the error? It's just the difference between the actual value and the forecasted value. There is another format or formula of the SES, which is the recursive form. Recursive form, look at it relies on the previous forecasts. So we have the upcoming forecast equals alpha times the current actual value plus 1 minus alpha times the current forecasted value, right? And alpha is between 0 and 1. And if you have high alpha, which is closer to 1, it's going to be fast learning. What does it mean by fast learning? It only recent observations matter. Because look, if this is very high, you just rely on YT, because this is going to be very small. If you have low alpha, close to 0, then it's going to be slow learner or slow learning. Slow learning, that means this is going to be closer to 0, and we are going to rely completely on the forecasted value, which is already relies on the previous actual values, right? So again, when we say slow learning, that means the new forecast depends mostly on the previous forecast. Older data keeps a strong influence, long memory, and the model reacts slowly to the new, let's say, new shocks in the data. That's why we call it slow learning. The fast learning is the opposite, which when alpha is 1, and the new forecast depends entirely on the most recent observation YT, and older data gets just very little weight, and the forecasts adapt quickly to any recent changes. So that's why we call it fast learner or fast learning. The typical value studies, or some of the books, they believe that the typical value of the alpha is between 0.1 and 0.2, and we are going to see this in examples. If you remember in our example, Amtrak ridership, we first difference the data twice to remove the trend and seasonality. Then what we did in the past, we did the moving average. Now, if we apply the SES, if we choose alpha to be 0.2, the ETS, by the way, the ETS stands by error trend seasonality. Error trend seasonality, and this is a function that we're going to use in R. And actually, ETS ANN. ANN stands for the adaptive error. This is trend, no seasonality. So we use this function. Now, in this example, we have an additive error and no trend, no seasonality. And in this example, if we fix the value to be 0.2 to the training data, therefore the validation forecast is going to be constant. So each month we are going to get negative 0.63. But to optimize alpha, and the technology can do that, the technology can optimize this value. Just if you ask the technology to do the best alpha value that minimize SE, it's going to do that for you. And in this case, alpha is going to be 0.0001, and we are going to see this. And the level is going to be 1.6. So this is the level. Look at the level on the validation data. This is a forecasted one. This is how the model behaved on the validation set. It gave us 1.6. Someone's going to tell me, what does it mean by 1.6? This is the level. If you want to calculate the forecasted value, you have to redo the differencing, etc. If you redo everything, you will be getting the value, the correct value of the forecasted value, or the validation value, the forecasted validation value. So it's like moving average. It's constant because we assume no trend, no seasonality, and we have multi-step here. So that's why f is equal to ft plus 1 all the time. So it's going to be just to be one value. And as we said, alpha can be estimated automatically by the machine. And the goal is to minimize RMSE on the training data. Sometimes we are worried about getting overfitting. So we don't want to have an overfitting model. So there is a link between both of them. Both of them balance recent values versus the old information with a single tuning parameter. One of them is the window width, moving average. The other one is the alpha, smoothing constant. And there is a relationship between them. W is approximately equals 2 over alpha minus 1. So this is approximately the case. So if W is a 3 weeks, 3 months, whatever, then alpha can be 2 over 3 minus 1. It's gonna give you this almost the same smoothing behavior. As mentioned earlier, both moving average and simple exponential smoothing should only be used for forecasting series with no trend or seasonality, series that has only level and noise. In this case, we can use these methods. One solution for forecasting series with trend or seasonality is first to remove these components through differencing, as we did before. Another solution, which is we will be talking about now, is to use more sophisticated version of exponential smoothing that can capture both trend and seasonality. And let's look at the problem with the trend in SES, simple exponential smoothing. Suppose that we have a time, 5 times, we have actual values. And if you want to calculate the forecasted value, for example, suppose that the level or the equation that we are creating, which is the alpha that we are choosing is 0.3. This is the forecasted value. ft plus 1, right? So we choose L to be 0.3, then this is 1 minus alpha, 0.7, this multiplied by yt, this multiplied by the previous value. So the actual yt is 100, so the level lt is 100, so ft plus 1 is 100, just nothing. We did nothing the first time. Then the second time, now we can see that L2 is equal to 0.3 times y2, which is 110, plus 0.7 times L1, because t minus 1, L1, which is the first one, actually, this one, L1. So 0.7 times 100, it gives you 1.03, 1.30.0. Keep doing that until you get the whole forecasted values for 5 points. And if you compare the forecasted values compared to the actual actual values are ahead of the forecast all the time. All the time. This is always ahead. 110, 103, 120, 108, 130, 114, 140, 122. So the actual values are always ahead of the forecast. And the problem, this is the major problem of SES, it's lags behind. So we are always behind because we rely on the previous values we take with. So the smoothed value LT is always below the true trend line. And again, to overcome this, we come with the HALT, which is double exponential smoothing, which is a linear trend. So if you have a linear trend, the question is, if you have a linear trend, what do you do? If you have a linear trend, we use HALT, linear trend smoothing. So what does HALT add? It adds a second equation that estimates the trend of the series and update it for every period. If you look now, we have two equations, one for the level, one for the trend. And the trend realized we have two now. We have two parameters. We have alpha, we have betas. So what does the level do? Adjust the baseline level, but includes the previous trend, t minus 1. To account for expected growth, the trend update measures how much the level changed since the last time, because we have LT minus 1 to show the difference between the levels. And smooth it out into a new trend estimate. So HALT can be used if you have data with a trend. So if there's a time series with a trend, we can use a HALT, which is doing double exponential smoothing. And this is an example about HALT. The same example. If you remember before, the forecasted value of the SES were always lagging behind, but now if you have YT, we have the level is 100, they have the trend is 10, just as an initial points. Then the FT plus 1, this is additive. Okay? We have an additive trend because we have multiplicative trend. So LT plus T is this plus this equals 110. Now apply these values to the second equation, second time, or the time period 2. We are going to get, this is LT, this is the trend. You add them, you get 120. So it doesn't lag behind. So compare the YT by the forecasted values. You will see that these values are not lagging behind. So again, why we are just using K is 1 here, because it's one step ahead every time, one step ahead. And why we are adding them, I'm using actually the formula. Yes, this is the formula. This is the forecasted value for the FTK. Okay, K is 1. So the error term can be additive, can be multiplicative. And if the error term is additive, we will be adding this. So the YT plus 1 is going to be equal to LTT plus ET. If it's multiplicative, it's going to be like this. And multiplicative error, if the error scales as a percentage of the level. So the variance grows with the size. But if it's additive, we are adding like a constant value. Okay. And typically here the variance is constant. Okay. We assume that the error follows normal distribution with the mean 0, standard deviation sigma, and variance sigma squared. But anyway, the whole idea here that we have to know that the error can be either additive or multiplicative, the same as the trend and seasonality. Then the question is what if you have seasonality? If you have seasonality, it comes to halt winter. Another technique, halt winter smoothing. Now, if we have a seasonal component, then we can use halt winter. So SES can be used to smooth if you have a level only. Halt can be used when you have a trend. Halt winter when we do a treble, exponential, and this can be used when you have a trend and seasonality both. And if you look at the equation, we do have trend and seasonality. Trend, seasonality. I'm not going to speak about formulas, by the way. And this, the trend and seasonality can be additive, can be multiplicative. These are just example about having additive trend, multiplicative seasonality. Additive trend, we add the trend to the level, then we multiply by the seasonality. In this case, we add the trend to the level, we add the seasonality to them. So we have additive in all the ways here, additive. Level plus trend plus seasonality. Level plus trend times seasonality, okay, not the periods. Yep, and these are just example about additive seasonality, multiplicative seasonality, and we talked about this one at the beginning. Linear trend, additive seasonality, multiplicative like a percent. We have the same behavior, but it increases or decreases based on a percentage wise. We have an exponential trend, additive seasonality, multiplicative seasonality, and we have damped trend, and this will be covered next lecture. Damped trend, it increases or increases, but at some point becomes like a constant. Like when it goes forever, it's going to be kind of closing to a constant value. Again, we have an additive seasonality, we have multiplicative seasonality. Also, we can think about having different errors as well. Finally, the last point that we need to know is how many types we have for ETS. We have many types. So if you count these are 15. 3 times 5, 15. 15 times 2 is 30. We have 30 types of ETS. Why they are 30? Because number one, the first one, Z is the error, okay? Z is the error here. So N, no trend, no seasonality. Z is the error, no trend, additive seasonality. Error, no trend, multiplicative seasonality, right? Let's say this, error, damped, trend, no seasonality. And here it's additive damped. Additive damped, additive seasonality, error again. Error, multiplicative damped, no seasonality, and so on. So these are 15, but what about the error? The error can be multiplicative, can be additive. So this can be A versus M. So this can be based on the error. So that's why we have 30 types of ATS. Luckily, when you do the work in R or the technology can actually adapt and can choose the best ETS method, and one of them is Tableau. Tableau actually uses ETS, and when you do forecasting in Tableau, Tableau does this for you and choose the alpha, beta, whatever, and the method. Sometimes you have yourself to tweak it to avoid overfitting. That's why human intervention is actually important to check the work. Okay, thank you.